The top coat isn't one layer, it's two. First is the base coat, a thin layer that contains the car's color and visual effects like metallic flakes or pearl scent pigments. On its own, it offers almost no protection. Immediately after, the clear coat is applied. This is the armor. It contains UV absorbers, chemical resistance, and scratch protection. Once cured, it locks everything underneath into a single bonded system. The entire vehicle is baked one final time, triggering chemical reactions that permanently harden the finish. And this brings us to the real secret behind modern paint. Old paints simply dried as solvents evaporated. Modern paints cure. During baking, advanced resins undergo a process called cross-linking. Molecules bond together, forming a tightly interwoven polymer network. The result is a coating that behaves like a single sheet of engineered plastic. Hard enough to resist stone chips. Flexible enough to expand and contract with heat. Durable enough to survive years of sun, rain, and abuse. All of this has to happen perfectly. Because if dust contaminates the surface, if humidity is off by even a small amount, or if one layer fails to bond, the entire vehicle can be rejected. That's why paint shops are some of the most controlled environments in manufacturing. And why robots now handle almost every step. What makes this process even more impressive is how unforgiving it truly is. A modern paint line operates inside environments more controlled than most laboratories. Temperature, humidity, airflow, and even dust levels are monitored constantly. A single airborne particle landing on the surface at the wrong moment can force an entire body to be stripped and repainted. That's why modern factories rely almost entirely on robots during the painting stage. Human movement creates turbulence, static, and contamination. Robots don't breathe, don't sweat, and don't make unpredictable motions. Every spray pass follows a perfectly calculated path, down to fractions of a millimeter. And even with all that automation, the process still isn't guaranteed. Paint behaves differently depending on humidity. Water-based coatings flow and evaporate at rates that can change hour by hour. Metallic flakes must align evenly to avoid streaking or blotches. Pearl scent finishes require precise layering so light reflects correctly from every angle. This is why certain colors are far more difficult to manufacture than others. Whites are surprisingly complex. Reds fade faster under UV exposure. Matte finishes offer almost no margin for error because they can't be polished to hide imperfections. Every color choice comes with engineering trade-offs. What most people never see is how much of a car's cost is tied directly to its finish. Painting is one of the most expensive stages of production. The equipment, the climate control systems, the waste capture technology, and the energy required for baking all add up quickly. In fact, the paint shop is often the single most expensive part of an automotive factory. And yet, it's also the stage customers judge the hardest. Scale gaps can be forgiven. Interior plastics might go unnoticed. But uneven paint, orange peel texture, or color mismatch instantly signals poor quality. That pressure is why manufacturers spend decades refining coating chemistry that most drivers will never think about. And here's the part that truly puts things into perspective. Every modern car carries multiple generations of chemical innovation on its surface. Accidental discoveries, failed formulas, fire hazards, environmental regulations, thousands of small improvements layered one on top of another. What started as furniture varnish evolved into one of the most advanced material systems in mass manufacturing, all to solve a simple problem. How do you protect steel from the world? Another detail most people never consider is what happens after a car leaves the factory. That paint isn't just designed for the showroom, it's engineered for years of real-world abuse. Road salt in winter climates, acidic rain in industrial cities. Sand, dust, and debris traveling at highway speeds. Even something as simple as automatic car washes slowly grinds against the surface thousands of times over a vehicle's life. Modern coatings are tested far beyond normal driving conditions. Panels are blasted with gravel to simulate stone impacts. They're exposed to intense UV light for months at a time to replicate years of sunlight. Chemical resistance tests involve fuels, oils, detergents, and bird droppings, all of which can permanently damage inferior finishes. At the same time, the coating must remain flexible. Metal expands and contracts every day as temperatures change. A finish that's too hard will crack. One that's too soft will scratch. Finding the balance between strength and flexibility is one of the most difficult challenges materials engineers face. This is also why repainting a car to factory quality is nearly impossible outside of the original production line. Body shops can match the color, but they can't recreate the controlled environment, chemical bonding, and curing conditions of a modern automotive plant. Once the paint is applied and cured at the factory, it becomes part of the car's structure itself. After more than a century of trial, failure, and refinement, automotive painting remains the most unforgiving stage of car production. Engines can be repaired, electronics can be replaced, entire interiors can be removed and rebuilt. But a flawed paint job often means starting over from the very beginning. That's why this thin, almost invisible layer of color is one of the most important engineering achievements in the automotive world. It isn't just applied for beauty or branding. It's engineered at a microscopic level to protect the vehicle for years under conditions most drivers never think about. Every curve, every edge, and every hidden seam carries the same responsibility: to shield metal from corrosion, to absorb impacts without cracking, to resist sunlight without fading, and to do all of this while remaining flexible enough to move with the car itself. So when you see a vehicle gleaming under the sun, you're not just looking at a finish. You're seeing the final result of chemistry, automation, and precision working together in silence. That shine isn't decoration, it's survival. Every car you see on the road is covered in a layer of technology most people never think about. It isn't the engine, it isn't the battery, and it isn't the steel frame holding everything together. It's the paint. Right now, more than 1.4 billion vehicles are in use worldwide, and every single one of them relies on a coating only a few millimeters thick to survive decades of abuse. Sunlight, rain, salt, heat, freezing cold, flying rocks at highway speed. And if this layer fails, the car fails with it. That's why painting a car is widely considered the hardest step in car manufacturing. One mistake can ruin an entire vehicle. And it took over a century of chemistry, engineering, and trial and error to get it right. At the dawn of the automobile, painting a car was painfully slow. Early vehicles weren't painted like machines, they were painted like wooden furniture. Workers brushed on thick varnish by hand, sanding and polishing between layers. Some cars required up to 25 coats, and the process could take more than a month. Even after all that effort, the results were disappointing. The finish cracked under sunlight. Moisture crept underneath. Within a year, many cars already looked worn and damaged. To make things worse, these varnishes dried so slowly that manufacturers were forced into a brutal compromise. Almost every car came in the same color, black, not because it looked better, but because it dried faster. But everything changed because of an accident no one planned.